Okay, now when we know how to derive the individual private and public keys from the root, and also how to convert the public keys to the addresses, we can receive bitcoins. Now it's time to get to spending these bitcoins and use our individual private keys to actually sign bitcoin transactions. First, I want to say a few words about the difference between transaction types in Bitcoin. So basically, we have two different transaction types, segwit and legacy. And the segwit, well, it's a pretty small soft fork though, so it's only slightly changed the serialization and signing procedure, nothing like super fancy there. So in particular, if in legacy transaction we had this number of inputs and number of outputs, and every input had the script seq that contained all the information for the script evaluation. So for example, in case of the pubkey hash transaction, it was a public key and the signature. And this made these transactions a bit malleable, so you could change the signature to another one that is also correct, and therefore change the transaction ID. And it is a little bit annoying, especially for applications like Lightning Network, where you are relying heavily on the transaction ID when you're building like this off-chain protocols. Then another thing is that when you are signing the inputs, you only relied on the previous script pub key. So you only had to know the actual script, but you were not binding to the amount that you are spending. So this means that if the hardware wallet wants to show you the fee, then it needs to ask the host for the full previous transaction, and then hash it, verify that it hashes to the right value, and then calculate the fee. And in case of the segwit transaction, first we get this flag that basically shows that this is a segwit transaction, and then all this information from the inputs, the signatures and the public keys, are going to the witness instead of the input. And this witness is not used to generate the transaction ID, so this means that the transaction ID will be the same for all valid signatures. In the input we have either an empty script seq or just the hash of the witness script for nested segwit addresses. And also when we are signing, we require not only the script pub key of the previous output, but also we require an amount. And this means that hardware wallet can just ask the software wallet what amount we are spending, and if the software wallet lies about this, then we will just generate invalid signature, and this means that transaction will be incorrect and it will not go to the blockchain. So it becomes way easier to calculate the fee in segwit transactions. Parsing the transaction for the hardware wallet are like the most important feature actually, because normally we do want to detect that particular outputs are the change outputs and hide them, and also we do need to know what private keys to use to sign these transactions. So what do we need in total? We need to show the user what amount he's spending, in particular what is the fee, what are the destination addresses, what amounts are going to these addresses, and if we have change addresses and amounts, then we can either show them or hide them, depending on our decision. So then we also need to know how to derive the private keys to sign these transactions, and also what script type is used. Because what we have in the hardware wallet is only the root private key, so we don't know which address, which private key to use to sign. And to make this all easier, there was a Beep 174 partially signed Bitcoin transaction format that basically is a raw Bitcoin transaction, unsigned transaction with additional metadata. And this metadata contains a bunch of useful fields. So for the global scope, we have our unsigned transaction. And in case of the multi-signature addresses, we also can have the XPubs of cosigners. And then for every input and for every output, we have some extra data. For the input, we have either the previous output, that is script pub key and the amount. And in case of the legacy, we need to pass the whole transaction. And this is very bad because if, for example, you are spending the output from the transaction that you where you get the money from the exchange, then this transaction can be huge, and then you need to pass this huge transaction to the hardware wallet, and it is annoying. Otherwise you couldn't calculate the fee. So segwit is really helping in that sense. Then what else we get? We get the redeem script and witness script if there are any. In case of pay to pubkey hash and pay to witness pubkey hash, there are no such things, so we don't need that. But for multi-signature and other scripts, we actually do need them. And then we also get the derivation path, is how do we derive the private keys for these particular inputs in order to sign. And then for the output, we can either get nothing. So in this case, it means that the output is going outside the wallet, so we are spending this money. Or we can get also the redeem script, witness script, and the derivation path, such that we can verify that, okay, this output actually belongs to us, it is going back to our wallet. So the change detection is a little bit tricky, because just having the derivation path is not enough. And yeah, recent vulnerabilities were showing that it is pretty hard. So Trezor, for example, had an issue with the change detection in the multi-signature case, and Ledger some time ago also had a problem where they just trusted and didn't verify the derivation path, so that you could also easily steal the money from the wallet. And with the code card, there was another issue. They were not checking the derivation paths, like they were checking the derivation paths that they belong to the wallet, but they didn't look into the indexes. And if you get some crazy indexes, that can be basically anything, you could actually lock the money of the user, and he couldn't get them back because he couldn't brute force all possible combinations of the derivation paths. So for example, if we have a particular input, and let's say it is a nested segwit with this derivation path, and we see the transaction that has certain outputs, which of them should we consider as a change output and which are not? Let's have a look at the first one. It is also nested segwit, and the only difference is like the last two indexes, where the this one is switched to 1, and it makes sense because this index is used to derive either change or receiving address. So this is the change address, great. And then the next index is the just the index, and you see that it is not very different from this one, so it's probably fine. Then let's say we can therefore say that this output is a change output. Then the next one is using also a pretty good path, but instead of the nested segwit, it uses native segwit. Here, well, it's a little bit tricky. I would say that it is still a change output, but it depends on the software implementation that you're using. So some software wallets only detect, only watch for a particular script types. So if you are using, for example, Electrum, then and you get this change output, then it will not detect it on the blockchain, and you will see that you're kind of losing the funds. But in Bitcoin Core, for example, you can set it up such that it is watching both nested, native, and legacy outputs, so you can still treat it as a change output. And Bitcoin Core actually allows you to use different script types for change outputs. So this is up to you to decide if it is a change or not. And then the next one. Here we see also the nested segwit, but the index is like crazy big, so it's very different from some of the previous one. So here, even though it does belong to the wallet, you definitely want to to warn the user that okay, something is wrong here. The index looks very weird. Please double check that you indeed want to do this. So this, for example, is the case where you do want to show the information about the change output. And then here also something weird happens with the derivation path. In particular, here we see the transfer from one account to another one. So if you remember, the last hardnet index corresponds to the account. So I would say that here you should show the user that, okay, you are transferring the money from your account number 0 to account number 1. Yeah, it's kind of change, but not exactly. Okay, and all this information we can get from the output scope of the PSBT. Great. Another tricky thing. So this is only like for single key path, single key scripts, and multisig is even trickier because there you have other cosigners and you don't have private keys of these cosigners, obviously, and you need to verify that your outputs actually belong to the same to the public keys corresponding to the same root keys as an input. So this means that you do need to get the information about the cosigners, and this is what we get in the global scope, the xpubs of the cosigners. You need to verify that the change output is belonging to the same to the private keys or public keys derived from the same master keys. So basically you have the input, you have the output, you verify that the input is derived from these guys, and then the output is derived from the same guys, and then the script type is the same, the indexes are not weird, and so on, and then you can treat it as a change output. So now let's implement the parsing and serialization and signing of the PSBT transaction. So I have here in Jupyter already the hardware device, so I can connect to it and import all the stuff that we need. In particular, we need the PSBT and base 64 conversion 2 bytes and from bytes. So I took all this PSBT transaction and the mnemonic from our examples. I didn't show it to you previously. So in the repository, we have the examples folder, and there we have a bunch of examples for addresses, HD keys, PSBT, and raw transactions if you want. And in the PSBT, I have this working example with the mnemonic, seed and root, and also with the PSBT transaction there. In principle, you can also use Bitcoin Core to generate the PSBT transactions, but maybe we'll do it in a different video. Okay, so we have this transaction here, and the first thing that we need is to convert it to the raw PSBT, like in bytes. So we take our base 64 conversion and convert this thing to raw bytes, and then we can print raw PSBT. And here is the thing. We have the magic bytes in the beginning of the PSBT, that is PSBT FF, and so you can easily detect that it is actually a partially signed Bitcoin transaction format. Okay, now let's see what is inside the transaction. First, we need to parse it. So we say transaction is PSBT parse raw PSBT, and let's print what is inside. So what we have here is a bunch of methods, but also we have this transaction. This is like a raw Bitcoin transaction. Then we have this unknown fields and xpubs for multi-signature, and also we have arrays of inputs and outputs metadata. So the inputs and outputs contain the metadata for signing and detecting the change, and the transaction itself, it's just a Bitcoin transaction. So first, let's calculate what amount we are spending. So this is a segwit transaction, so all the inputs will be segwit inputs. So total amount, total spending, let's say 0, and then for inputs in transaction inputs, we do the following. We take the input and let's see what is inside. Let's say we do dir tx inputs 0, inputs 0. And here we have witness UTXO, so we can take witness UTXO, and then if we look what is inside witness UTXO, we have the value. So we want to add this value to total spending. Okay, and then let's print total spending is this. Great, now let's do the same for the outputs and calculate the fee. So the outputs that we total out is 0. The outputs that we want to look at are actually inside the raw Bitcoin transaction, because it's not in metadata and it's actually in the transaction itself. And there it is not called outputs, it called VOUT, because in Bitcoin Core it is called VOUT, so why not? And then we do total out plus out value, out script pub key, I think. Nope. Just output value. Yes. So this is the total output that we are spending. So therefore, our fee is just the total spending minus total output. And so let's print fee. So fee is 2000 satoshis, and input is like 2 bitcoins. We can just divide it by 10 to the 8 and see how much it is in bitcoins. And the same we can do here. It's 1.99. Okay, so now we know the fee, and it's time to check what are the outputs. So for every output, let's print the address and the amount first. So for out in txt out, print let's see what we can do here. So we do output script pub key, and we need to pass to get the address from it, and we will use networks rectest. Okay, so this is what we got, and also let's put a value here. So we just do output value. So we have these addresses and these amounts that we are spending. Now we need to understand which of this output is a change output and which of them is not. Okay, so for this we have some additional metadata in the output scope. So let's say we do for out in tx outputs, print out. Okay, we have two output scopes, and we can do print dir output, so we can see what is inside there. So we can have this BIP32 derivation. Okay, so let's print outputs BIP32 derivation, and in case of the first one there is nothing. So the first one is definitely not a change address, and then the second one is maybe a change address because we have some BIP32 derivation, but you shouldn't trust it. So you definitely should verify that it is indeed the right thing. Then what we do, we will check the following. So for key in this derivation, the key of the derivation is the public key. So you can verify that this public key is actually getting to this address. And we can also verify that this derivation is used to can be used to get this to this public key or to this private key. So what we do the following. So we take our derivation path. So it will be derivation is like this. And then here we will have two options. We will have either the fingerprint. This should be the fingerprint of our root key. And we also have the derivation that will be an array of indexes that we can use to derive this public key. So let's print this derivation. So we have, for the second output, we have these indexes, and these are the hardened indexes like 84, 1, and 0. And then we have 1 that is a change address, and then 0 is the index. So now how do we derive it? We just do the following. So our private key will be our root, derive, and this derivation. And then our public key will be private key get public key, I think. Let's see, and let's print pub. Okay, no, there is no such thing as get public key. So then instead let's nope. Okay, so let's see what we have in the private key. So we have there to public. Okay, makes sense. So to public, and then this will be our public key. Right. So this thing is this private key is actually an HD private key. So we need to convert it into the private key, or we can just convert it into the public key and then get the key, and then this will be our public key. Okay, this is the public key, and then we need to compare if this public key is equal to the key of this dictionary. Okay, so they are the same. Great. This means that actually we can derive the corresponding public key. And let's say change detection. Change equal to false. Then here, if public key is not equal to key, and then we just break, and it is still not the change. Maybe if there are multiple derivation paths, we will actually want to continue. And then if everything is fine, but it will eventually do the same stuff, and if everything is fine, we need to verify that this public key corresponds to the right address, to the right script. So we do the script, that is the script pay to witness pub key hash of our public key, and let's print script address networks rec test, and we just print it. Okay, so we see that this address is actually the same as this address. So what we did here, we verified that we can generate the public key from our root private key here. And then we checked that this public key is actually corresponding to the script pub key of our output. So how do we do it? We want the index and the output, and just enumerate that to get the index as well. And what we compare this with, we need to compare if script not equal to, well, if script equal to the txtxvout script pub key, then change equal to true. Okay, and then for each of them, let's put this here as well. If pub equal to k and like this, then this is the change, and then we can print if change, then we print txtxvout I script pub key address networks rec test, change, and then else we print that this thing is spending. Okay, so spending this, change this, great. And also let's put the amount here. So txtxvout and value. Okay. Okay, great. So now basically what we have the spending output and the address, and we have the change output that we verified and the corresponding amount. So for multi-signature and for complicated script, it can be a little bit tricky. And also we didn't use all this redeem script and witness script here because we only parsed the pay to pub key hash. But basically you can extend this function to verify also the redeem script, the witness script, and the multi-signature, the cosigners, and so on. But it just takes takes a bit more of programming, and this logic will become a little bit complicated. And I hope that you got roughly the idea how can we parse the Bitcoin transaction. So now when we parsed it, so we basically can show to the user that, okay, we are spending 2 Bitcoins, the fee is 2,840 Bitcoins, and we are spending it 0.3 Bitcoins are going to this address, and then this is the change that is going back to us. Now if the user verifies and confirms that we need to sign this transaction, we can just sign it. And signing is very simple, so we can do tx sign with and our root. That's it. And now if we print tx, serialize, this is our serialized transaction, and we can actually see that after if we look at the tx and then let's see what is inside, there is this input thing, let's say input 0, and there is this partial sig thing. So let's go to partial sigs, and for the partial sigs we have we can just print them. And this is the public key and the corresponding signature. So we basically included into the PSBT the partial signatures for the keys. In our cases, we are using a single key. It actually is all the signatures that we need. We only need one signature. And so then we can send this PSBT transaction back to Bitcoin Core, and Bitcoin Core can finalize it, combine it, and then broadcast it. Let's first put it, serialize it not as raw bytes, but actually as a base 64 string. So what we do B to A of this. Okay, great. This is our transaction, and we can copy it, and we can inspect Bitcoin CLI, reg test, finalize PSBT, and this. And here it is finalized, so it shows us that it is complete. And so now we can actually use this hex to broadcast it. So I doubt that it will work here because I don't have this wallet and I have a different reg test. But in principle, then you can just broadcast it and it is done. Okay, so now we already have a working piece of code that can parse transactions, display us all necessary values, verify the change addresses, and also sign the PSBT transactions. And from here we can go and implement a full hardware wallet with the GUI and stuff. I will talk a bit about that, how we can continue from here in the next video.